A moving coil galvanometer is a highly sensitive instrument used to detect and measure small electric currents. It works on the principle that a current-carrying coil placed in a magnetic field experiences a torque. The pole pieces are made concave and a soft iron core is placed inside the coil. This creates a radial magnetic field, ensuring that the magnetic moment of the coil is always perpendicular to the field lines for maximum efficiency. When current flows through the coil, it experiences a deflecting torque. Because the field is radial, the angle theta is 90 degrees, simplifying our torque equation to the number of turns times current, area, and magnetic induction. As the coil rotates, a fine hairspring attached to it winds up, creating a restoring torque. This torque is directly proportional to the angle of twist, represented by the torsional constant K multiplied by the angles phi. The pointer stops moving when the deflecting torque equals the restoring torque. At this equilibrium point, the magnetic force driving the rotation is perfectly balanced by the mechanical tension of the spring. By rearranging our equilibrium equation, we see that the current is directly proportional to the angle of deflection. This linear relationship allows us to use a uniform scale to read the current measurements. Current sensitivity is defined as the deflection produced per unit current. To increase sensitivity, we can increase the number of turns in the coil, the area of the coil, or the strength of the magnetic field. Voltage sensitivity is the deflection per unit voltage applied. Note that it depends not only on the coil's physical properties but also on its electrical resistance R. Increasing turns doesn't always increase voltage sensitivity if resistance increases proportionally. The soft iron core serves two purposes: it increases the magnetic flux density through the coil due to its high permeability, and it helps maintain the radial nature of the field for a linear scale. To make the galvanometer deadbeat or non-oscillatory, the coil is wound on a metallic frame. Electromagnetic damping caused by eddy currents in the frame brings the pointer to rest quickly without excess swinging. In summary, a sensitive galvanometer requires a large number of turns, a strong magnet, a large coil area, and a suspension fiber or spring with a very small torsional constant. The moving coil galvanometer remains a fundamental tool in physics for detecting weak signals. By balancing magnetic and mechanical forces, we achieve precise measurement. Generated by Vision Solve AI.